we are working on quantum cybersecurity and more specifically, quantum resilient cybersecurity. Something that we provide in the market right now as a SaaS platform, and it's really there to and designed to take us into the next generation of security, more specifically around data security and keeping it out of unauthorized hands. And the reason we do it is because, based on the rate of progress, at least according to Morgan Stanley, and they're actually quite right. This is a statement that they issued a couple of years ago. But the short of it is that quantum computing is evolving significantly faster. And I'll endeavor to give you a quick, 5-minute PhD in quantum. And also talk a little bit about how it relates to us, in the industry, and what is being done about it, and what we're likely to see coming up from the industry itself over the next couple of years. So, having said that, I want to make sure that we understand what quantum computing is, what it does, and what it doesn't do, and what its implications are, very specifically. So when we look at traditional computing, we're looking at our classical systems that are based on our typical microprocessor architecture, but essentially what we're familiar with is the fact that they calculate everything in ones and zeros, in binary. What that means is that it's actually a linear process, and a very a specific one based on how the computers can actually process data. So what happens is they have a word size, 64-bit word size, for example, and it goes out and it starts interrogating each calculation in the CPU linearly, one by one. And what that means is it takes a long time for us to process anything. So when you plug in a map in Google Maps, for example, it will go and start looking at all of the different possibilities of how you can get there, and then select and choose the most efficient route for you to get there. So you decide to make a wrong turn, or you decide that you know better than what it does, and you will see it take a few seconds to update that navigation, to update those instructions. And it's doing it because it has to go back to itself and then start looking at what happens from this point on, because this is unexpected, and now I need to recalculate everything else and come back with a new set of results. So essentially start from the beginning. And there are a lot of uses around that, but the difference between those systems and the way quantum computers process is because in the case of quantum computers, they are actually able to look at the entire data set because of the fact that they calculate both ones and zeros simultaneously. In other words, it essentially sees all of the possibilities all at the same time. Because what happens is when you measure it, the results that come back to you are based on where that result is right now, and it could be in any kind of a state. And more specifically, it's not even based on the 1 and 0, but it also includes the spin and the momentum and so many other components of a quantum system, depending on how it does it. And it does it based on physics principles of superposition and entanglement, and we'll talk a little bit more about that in a second. So the reason it comes out in the news so much is because in the case of quantum computers, by being able to look at that entire data set, we can actually calculate and break things down very easily. The benefit of it for the general industry is once they get powerful enough, we'll actually be able to do things completely differently to the way we do them now. We can look at and analyze very large, very complex data sets also for a number of different industries, and be able to approach the problem in a very quickly. In other words, if we want to make a new type of material, what we would be able to do in the next, when the quantum computer is mature enough, is we'll be able to say, I want to create a material with the following properties, come back to me with results. The way we do it right now is hypothesize what the material is going to be, iterations, a number of making that material, and we started by eliminating all of the bad ones. So, we're all familiar with that old story, how Edison created the 9,000 ways of not having a successful light bulb until he created the one successful way of creating a light bulb. This is essentially what we do now for across the board, for medical compounds, for imaging, for anything else. For when we create medicine or when we create materials, we just look for a new type of material and eliminate all the ways it won't work. And quantum computers, by looking at that entire data set, will actually be able to come in from the completely opposite direction and give us the results that we want. Because of these very aspects of being able to look at the entire data set, the entire problem space, and eliminate all of the possibilities in a nonlinear way. Now, what they don't do well is linear processing. So anything that does require an iterative process is where our classical machines will still continue to be the preferred method of doing things. But the other part comes down to the compute power and the processing power of quantum. And this is really when we start getting into the algorithms and the security behind quantum computers. So, funny enough, a side story. We actually see quantum processes in our daily lives all the time. For example, a leaf, when it processes sun's energy, it actually uses a process that's a quantum process rather than a classical process, because it actually, as the sun hits it, everything, all of the energy is actually being generated all at the same time, and then it flows into the stem and gets converted to energy for its own use. So, but what does it mean to us in the industry, especially around security? Because our existing way of protecting data, our existing way of protecting everything that we do, everything that's precious to us, is through cryptography. It's our first, and it's also our last line of defense. And we use it when we transmit data. We're using it right now in this video stream by using HTTPS, or in other words, the TLS protocols that we're running here. But we also use it to encrypt stored data. Data, while it's being used, sometimes gets encrypted and used in an encrypted state. So it really becomes that crucial point for us where we've been relying on for a long time. The unfortunate thing is we're relying on technology that's 40 plus years old in many ways, and it hasn't evolved much ever since. So by having a processing or compute power that will actually look at all the possible variants simultaneously and break them down, well, that affects the way we build our cryptography, because for data in motion, asymmetric cryptography, we use prime number factorization. That's what the RSA algorithm is. That's what ECC is. Both of these families are designed specifically around prime number factorization and some other mechanisms that we use. And what that means is, and the reason why we see it in the news so often is because Shor's algorithm is able to break that down. And that's not a theory, that's actually a fact. I've actually seen it with my own eyes from our own research team, who have been able to break 8-bit numbers using very small quantum computers. And right now we end up waiting for a cryptographically relevant, a large enough quantum computer to come online. And incidentally, for this Shor's algorithm attacks on prime number factorization. The little bit of math here is the formula to break cryptography is 2n plus 3. And the 2n really means the strength of the cryptography itself. So, for example, 4096 or 2048, multiply that by 2, add another 3 qubits, and that's really the power that you need to break cryptography, to break asymmetric cryptography. So, because we transmit our data encrypted that way, it becomes a compelling enough reason to move to something better and to move to something much more resilient. But of course, there are other attacks on symmetric cryptography. That's our AES algorithms, that's the CHA-20, and so many other ones. But those ones that don't rely on public key cryptography, that use the same key and transmit it safely for storing our data primarily, although it's used in many more ways than that. That one is actually simplified by a factor of 2 using Grover's algorithm. Grover's is very interesting because it was designed to be an exhaustive search algorithm to look at large data sets and calculate out and process large data sets. But what the industry's found is that we're actually able to use it to simplify that very crucial part of encryption. And when we say simplify, since most of our encryption uses 128 or 256-bit encryption, 128 gets broken down to about half, which is no longer considered to be secure, and 256 gets broken down to 128, but then it becomes only a matter of time until that's assailable also. So things should be done around that. And we can dive into the nuances a little bit later. So what does it mean in practical terms, right? Because we need to be able to use it, and what the defenses that we typically talk about is, well, if we increase what happens if we double the strength of encryption to make 256 a 512, get rid of 128, and still rely on the 256 as the lower mode for encryption, the lower strength, and change our paradigms around that. The issue then becomes what happens to the processing power that is used to work on those workloads. In other words, when you double the bit strength of that kind of encryption, you're actually increasing the compute power that you need to decrypt it after the fact, to be able to use that data. And and by increasing that time frame, you're actually expanding how long it's going to take you to decrypt that data, and that will impact SLAs, that will impact just the general experience. So then we get into a race of, what do we do with legacy equipment? What do we do moving forward? How much compute power do we need for growing data sets and data warehousing and so many other practical implications. So let's frame the problem in slightly more concrete way. Every day we deal with data and how to protect it, and there are some entities that are very vested in getting that data decrypted. As a matter of fact, when you're dealing with nation state and nation state attacks, and we've seen time and time again, nation state sponsored or people who have those types of skills are actually going after private industry. It's not necessarily being done government to government basis, but it's actually being done on nation state to corporate, to steal intellectual property, to steal research and development, to steal data, to run analytics on behavior and behavioral patterns, and just cause disruption and havoc. So the nation state players that we deal with, they do have their own Oppenheimer. They've dedicated a lot of resources around this very fact and breaking cryptography, and really are there to capture as much data, as much information as they can, because that data then can be broken and can be used and can be distributed. So, and of course, as we continue to grow our own data points, and I can see that it's becoming a recurring theme for us. Everything is about data, but everything really is about data, and it increases the attack surface. The legacy systems need to be addressed. Funding needs to be there. The general push needs to be there. But fortunately for us, we're actually seeing that traction. White House has been doing a lot of pushes. There's been a presidential memo released quite recently to fund this research, to really fund all of the development and getting it into industry's hands. There's been a lot of support from both Congress and House side of the government. And of course, budgets are being allocated to these efforts. NIST is working very hard on it since 2015, and I'll talk more about that in a second. And a lot of government agencies are now required to, at the very least, understand where they are cryptographically, and do something about it, to really understand their path to becoming much more secure as well. Because we are seeking to counter new attacks, especially with an expanding attack surface, become a lot more resilient, both as an industry and as a government. And of course, we're always trying to eliminate data breaches, prevent losses, prevent remediation costs. If we can avoid that, reduce our insurance would be nice. And there is a lot of that support going on. So that's the good news. So let's talk about the approach a little bit. Traditionally, every time we do a cybersecurity audit, we've looked at controls. We've looked at how we're protecting our people, how we're protecting access to data. Is the data itself being encrypted? But we've never really looked at encryption as an industry very much. We'll look at risk, we'll look at risk mitigation, and encryption becomes a checkbox. So failures in implementations, failures in the right types of algorithms that are being used are actually quite common, and and some of them are actually the reason why TLS 1.1 shouldn't be used anymore. It's considered to be completely vulnerable. There are so many attacks and families of attacks around TLS 1.2, which is still the predominant data in transit algorithm that's being used publicly, and even TLS 1.3, which has low adoption but is much stronger, has its own set of vulnerabilities, and they're all well documented within CISO and other organizations. So the opportunity for the commercial sector actually becomes a major opportunity for us to really step up, and look strategically of what are we doing, how are we managing our data, are we doing the right things, and of course with NIST, having been working on it since I believe 2015. They were originally looking to release new algorithms and update the FIPS 140-2 standards with 140-3, and really take that to the next level. They were originally planning to do it in 2025. Now it looks like it's going to happen much sooner than that, and the research is going well. We've actually found new vulnerabilities that are being addressed in the quantum resilient algorithms, and that means because of the vast amount of peer review, because of vast amount of support for all of these things, the algorithms that do come out will actually be much more resilient than anything that we use in the market today. And of course, because of its uses in the market, we're looking at not only the traditional ways of storing data or communicating data, but the entire blockchain is built on digital signatures, and digital signatures are just another form of cryptography, and it's another form of cryptography that needs to be resilient because we protect so much of our data and so many of our assets, more specifically, using this. In other words, when we created blockchain as an industry, we trusted that because of its cryptographic basis for storing data, which meant that we can open it and use it in public. The way it's been accepted in the industry itself is that we've placed a lot of extrinsic value in blockchains themselves, which of course means that for an attacker to erode trust in the blockchain can actually cause a complete collapse, not only of the blockchain itself, but also in the financial vehicles and other vehicles that we've placed and put value around that blockchain. So even those methods need to be protected and really become quantum resilient. And so we do really need to move as an industry and really need to continue to grow and excel. And we do that because any data that has been stolen from us, and we read about it in news all the time, right? It's become a daily occurrence that someone got crypto locked and all of their data is locked up. But that also means that all of their data has already been exfiltrated from them, and they can be held for ransom twice: once to get access to their data, and once to make sure that that data stays somewhat safe and somewhat private. But then, of course, we're trusting an untrusted source, right? The attacker. Nation states have harvested as much as 25% of all of the globally encrypted data, and are working to break that, because that data is valuable. It carries so much useful information, and so much more useful information can be derived from it by processing it and running data analysis on it, even as data itself goes. So because of that, the store now, decrypt later types of attacks are really something that we need to address, and we need to address quickly and adequately as an industry itself. So there are many things that we can do about it. We can actually implement new processes and new procedures, but we can actually address a few fundamental areas that have never been addressed before by going and looking at these new forms of cryptography. So I've already spoken about the NIST approved algorithms and a little bit on their timeline, but that is just one piece of the puzzle. And this is the piece of the puzzle that we've looked at the most as an industry every time we implement some sort of cryptography. Because by implementing the TLS protocols, we use the algorithms that have been approved and validated by NIST and peer reviewed very heavily. So we kind of know about this as an industry. and the next step is, of course, to take those quantum resilient keys coupled with the algorithms and make them truly quantum resilient, which means resilient against attacks by quantum computers. But we really need to look at how those keys move. So trusting in the TLS processes, which are based on RSA and ACC algorithms, and public keys, the PKI infrastructure, that is due for its own revamp. It needs to be changed, because even the certification authorities have been known to be breached, which means that all of the keys that are generated by them, all of the public keys, are inherently insecure from the get-go. So that trust that we place in it, the little green lock that we see at the top of our browser, is not necessarily quite as safe as we hope it would be. And because of that, companies like Apple, Microsoft, and others no longer allow long length of keys. They're trying to mitigate that risk by reducing the time that a key can be alive from 5 years or longer of what it used to be down to 1 year, sometimes less. But that's not all, end all be all, because we can actually also look at how the keys are seeded and what kind of entropy source is being used to generate those keys. So no longer do we generate those keys on processor on the same device that we're using that generates data, but maybe take it offline, out of band, or out of process, and actually focus more on key delivery. That way, an attacker who gains root level access or manages to get in at the hardware level is still not going to be able to force errors or control the key generation process itself. So we can actually keep our data more secure, even as attackers become better at what they do. So that key delivery, the mechanisms themselves, the trust built around it between different devices or between different entities like users and devices, becomes much more paramount as we proceed down this path. And of course, those protocols, we can introduce a lot more protections in there, and that's one of the things that we've been working on, even into the protocol itself, and how it manages to create a much more difficult process for the attacker by injecting other keys and rotating them and bringing that true cryptographic agility even in the data communication process itself. And the last thing that we haven't done as an industry is we haven't really monitored cryptography and really monitored it behaviorally and in the process to remediate attacks. And this is something that becomes a really big deal and a great opportunity for us to continue to evolve. And that's all that way because the vulnerabilities are there. We fight a very asymmetric type of a warfare with our attackers, because the vectors into our networks are continuously expanding, and we can't continue to chase vectors. What we need to do is actually focus on the assets themselves, the things that are most valuable to us, and really work to protect the asset, the value, because it's much easier to identify what's important and put in all of the defenses on that side of things, rather than trying to chase ghosts and outguess what the attacker is going to be able to do there. And we can do that with true cryptographic agility, which means key rotation, algorithmic rotation, and management, being able to replace the keys on the fly, being able to inject them where we need to, and being able to use a true quantum process to generate that, as well as monitor for anomalies and do so many other things. And what we don't need is a full quantum computer to do all of these things. As a matter of fact, we at QuSecure are doing it using a PCI card that runs a quantum process on it using regular servers that are racked and are your typical commercial everyday servers that can be used and integrated with all other mechanisms around data management, data movement, devices, users, user accounts, and so many other things. And we do that by focusing on the entire data lifecycle as a holistic entity, because data gets generated, it gets used, it gets transported, transformed, and it has its own end of life cycle. So sometimes we need to protect that data for 7 years at the completion of at the closure of an account, and sometimes it needs to reside for 75 years to a lifetime, depending on what kind of data it is. So we'll look at network infrastructure, systems, storage, applications, and how they're used, and of course devices themselves as part of it. So having said all of that, I'll wrap it up and see if there are any questions. Should probably stop sharing my screen.
Thank you so much for that. Wow, it's a very important topic there that you're covering, and one that's really relevant to today's world.
Thank you. Yeah, it's funny. I typically
decided not to work for me.
Pardon
Apparently,
me?
right on cue here. There we go. I think that they're in now. Okay, are you hearing me better now?
Yeah, I hear you really well. Can you hear me? Okay,
Perfect.
great.
Yes, sorry about that.
No worries. So, you know, I usually get questions around why, how long will it take for quantum computers to really become cryptographically relevant and be there, and what timeline do we have, what timelines we're working with. So I can jump ahead a little bit to that, since the audience is being a little bit quiet. I'm not seeing any of the questions pop up, but
yeah, that'd be great. That'd be great to answer that.
Yeah. So there are different schools of thought there. A lot of the scientists that work on quantum machines say that it could be as long as 10 more, 20 more years. That when they become relevant, but we're already seeing some data that's that looks like it's already been broken, and it could only have been broken by quantum machines. So the other part of it is in the commercial sector, we're actually seeing a lot of advancement going on with, and we expect to see within the next couple of years true cryptographically relevant machines really come online. And they're becoming much more accessible. IonQ is well on track for desktop size quantum machines that will give us a real taste into what we can do. There are so many other technologies there that are maturing. The good work by the guys at Atom Computers will really bring to market really powerful machines, and they're also well on track within the next few years to start delivering it. And we're seeing more and more traction in the market. And there's been just so much research using different methods to build quantum computers, from photonics to ion traps to so many other methods. CMOS architectures are being developed, which are everyday room temperature computers, and many of them don't look like the typical chandeliers that we see in the news. So it's a very interesting world now.
It is indeed. Definitely. Well, I keep asking, like I said, I keep asking this question, but I'm loving the responses that come out of it. Given what you've lived through now, are there, 3 pieces of advice that you'd like to impart to the audience to help them not have to live through similar challenges?
Yes, of course. So One of the biggest things that I got out of my career is actually looking at all the problems that face you daily, but actually be able to take a step back and look at it as a greater whole. Because not every problem needs to be addressed immediately. Sometimes it's better to take a step back and think about it strategically and see what can you do that will actually address today's problems that are facing you right now, but also tomorrow's problems, so that you can actually start getting ahead of the game. And that really reduces the load both on you and on the teams that you run, teams that you manage. And being able to take that step back always and proves to be really worthwhile. Other than that, it's a lot of it comes down to maintain focus, better perspectives, and just really being able to prioritize what you do, how you do it, and tackle it with keeping the future in mind.
Right. How do you have any tips for how you do that prioritization?
Oh boy.
I'm asking the hard questions now.
Yes, you are. It's well, I'll tell you what doesn't work. Flying by the seat of your pants really does not work. But being able to frame the problem and really look at what the strategic impacts are and how to prioritize those strategic impacts, and working out what's important versus what's urgent, and really focusing on what should be done to create an optimal path to goal, to achieving the objectives that you want to achieve. That proves to be very useful.